After finding out how much energy goes into or out of a system, the next question is figuring out how that energy affects the system. This is usually manifested in terms of a temperature change. The amount of energy it takes to change the temperature of a substance is measured by its specific heat. Officially, the specific heat is the energy required to raise the temperature of a substance by 1 degree per unit mass. This can be rearranged so that the value of the specific heat, denoted by C, is the change in energy input divided by the change in temperature, or since the incoming energy is usually in the form of heat and changing the deltas to derivatives, the specific heat is the partial derivative of the heat added per unit mass with respect to the temperature, or partial Q partial T, as seen here. These actually depend on the process. There are two common types of processes in thermodynamics, those which occur at constant pressure. These are typically ones that are open to the atmosphere and therefore remain at atmospheric pressure. And the other type are those which occur at constant volume, usually things placed inside a rigid tank. Therefore, the specific heats are denoted by subscripts, here P or V, indicating those processes. As mentioned, these have different values, with Cp always being bigger than Cv, as the constant volume does not allow for any expansion, which itself takes up energy, and therefore energy that cannot go into the heating of the substance. For a closed system, we know that the change in energy, U, is the heat, Q, minus the work, W. Note that this is all per unit mass. So the amount of heat added is the change in energy, Du, plus the work, which can be expressed as PdV. Although if we have a constant volume process, then dV is 0. So it simply becomes dQ equals du. Going back to the definition of specific heat, the heat added divided by the change in temperature. This can be expressed as this derivative, partial Q partial T, or partial U partial T. In terms of notation, this is C sub V, indicating a constant volume process, as well as the V subscript outside the derivative. And since all variables are lowercase, they are all per unit mass, except for temperature. Similarly, for a constant pressure process, we can perform the same analysis. The difference here, though, is that the process is not constant volume, so dV is no longer 0. This means that the heat added is not equal to the change in energy of the system, but rather equal to the change in enthalpy of the system, dH. So the specific heat at a constant pressure is given by C sub P equals partial H partial T. Specific heats are dependent on the substance, so different materials have different values. This means that things like metals with a lower value of C heat up faster than things like water, which have higher values. The specific heats themselves are only mildly dependent on other properties such as temperature and pressure. So depending on the range of temperatures, it may be okay to use a single value, or if there is a very large temperature change, it may be necessary to take this variation into account. Usual units for the specific heats are change in energy per unit mass over change in temperature, so joules or kilojoules divided by kilograms and Kelvin or Celsius, or in the US system, BTU per pound mass, degree Fahrenheit, or Rankine. There's another option for the specific heats. Instead of per unit mass, they can be on a per molar basis. These have bars over them to distinguish them, and in terms of units, have mass terms replaced by kilomoles. There are a few cases where we can go into a bit more detail about the way the temperature changes with the addition of heat. The first of which is ideal gases. Here we know that the pressure times specific volume is equal to R times temperature T. The internal energy, U, of an ideal gas is only a function of temperature. So starting with the enthalpy of H equals U plus PV, this can be replaced with U plus RT. And since R is a constant, we can see that H is a function of only temperature as well. Again, based on the definition of the specific heats, the equations can be rearranged so that the differential change in energy, du, is equal to Cv times dt, and the change in enthalpy, dH, is equal to Cp times dt. Note that since these are now full derivatives, instead of the partial derivatives in the official definition, these can be integrated to find the actual changes in specific energy or enthalpy, as seen down here. These integrals vary in difficulty when it comes time to actually evaluate them. As mentioned previously, there are circumstances in which the specific heats can be treated as constants. These are generally when the temperature changes are small. In these cases, the integrals simply reduce to this value of the specific heat times the change in temperature. For the harder cases, when the specific heats vary with temperature, there are a few options. For most substances, there are either graphical or tabular data for the values of C at various temperatures. These can be used to integrate the functions. Or sometimes these tables have the integrals worked out already, so that all that is needed is to find the appropriate values in the tables. Another good approximation is to take the average value of the specific heat over some temperature range. This way, the integral again reduces to a simple change in temperature times this average value of the specific heat, as seen down here. We can play with some of the equations for ideal gases, mainly starting with H equals U plus PV. We replace PV with RT. Then the differential of this is dH equals du plus RdT. Then dividing by dt, Cp equals Cv plus R. Or on a per molar basis, instead of per mass, we have Cp bar equals Cv bar plus fancy R, 8.314. A quantity that becomes useful, and we will see in later thermodynamics analysis, is the ratio of these two specific heats, denoted by K, and is equal to Cp over Cv. For monatomic ideal gases, K equals 5/3, while for air, K equals 1.4. This is technically only at room temperature, but as mentioned before, both Cp and Cv don't change much with temperature, so using 1.4 for air is usually okay, as long as the temperature is not really high. Or low, for that matter. As for solids and liquids, their specific volumes do not change much throughout any process. It would take an enormous change in pressure or temperature for the volume to change substantially. Therefore, we do not need to distinguish between Cp and Cv. For these substances, generally there is only one value of the specific heat, denoted just C, as can be seen in table A3 for some common liquids and solids. The change in energy can be evaluated exactly the same as we saw for ideal gases. Either take into account the variation of C with temperature, which may need to be done for large temperature variations, or treat C as a constant, either as a single value for small temperature changes, or as the average value over a large temperature range. The change in enthalpy becomes du equals dH plus vdP plus pdV. And again, we can ignore the change in volume contribution, so dH equals du plus vdP. Then we have seen how to deal with the du term on the previous slide. The easiest way is to use the average value of C, so that delta U equals C delta T. Now for solids, there is no significant contribution from any change in pressure. So for solids, we have delta H equals delta U equals C dt. For liquids in general, we have the same equation above, this one here. However, there are two common scenarios in which we can make some simplifications. One of these is for a constant pressure process, which is the case for heaters. In this case, delta P equals 0. So we're back to the same case here that we saw for solids. The other common process is a constant temperature process, which is the case for pumps. Since delta T equals 0, delta U would be 0 as well. So for pumps, the change in enthalpy is reduced to delta H equals V delta P. And as you should be used to by now, ending off this video with your pre-lecture example for the day, along with the answers. Please bring any questions you may have to class as usual.